Okay, so this is the second lecture of this operating system course, and in this lecture we'll cover some fundamental concepts in OS. We already have been introduced to the basic idea of an operating system. What is an OS? We saw that in the last class. We also had an idea about what are the goals of an operating system. Today we'll talk about some fundamental concepts, and we'll try to relate that with whatever we covered in the last class. So let us begin. This is what I'll be covering in this today's lecture. We'll look at some fundamental concepts, which includes the idea of booting. Booting is the process of loading the operating system from the secondary storage device to the primary memory. Then we'll talk about a concept called process. I'll introduce you to this particular concept because we'll see this working with process in more details in the subsequent lectures. As you know, in the last class, I introduced you to a concept called system calls, and we know that this is the way by which an operating system, an application interacts with the OS. So what exactly are system calls? How are they executed? And what is the relation between an interrupt and a system call? So we'll talk about all this in today's lecture. Well, so this is what we had covered in the last class. We discussed about the basic idea of an operating system. Why is it used for? And if we can summarize the basic goals of an operating system, it can be done using these 3 points. So what is OS? OS is a middleware that is used for efficient use of the computer system, or it allows the users to efficiently use the computer system. How? So it provides, or it has 3 goals. The first goal is it allows the user to use the computer system in a fast and efficient manner. One of the ways of doing this is through something called abstraction. As the name implies, it abstracts or hides a lot of things. For example, in a computer system, we often would like to access some input-output devices. These input-output devices are of varied types. Each has its own way of access. Thus, if an application or a set of applications, if they have to access a particular IO, the access mechanism of each IO should also be included in the program, which means that every user or developer of a particular application has to know the details of every individual IO that is going to be used. So if I am a user, if I have 5 different IOs to be accessed through my program, I have to know each and every detail about all those 5 IO. This is tedious for the user. So in order to facilitate the user and remove or reduce the burden of the user, the OS is a collection. It's a collection of utilities, which includes the access mechanism of all different IOs, is provided to the user. So the idea is that if a particular program wants to access some IO, say this is a program P, and there is some IO that needs to be accessed. So some instruction of a particular program, if there is a requirement for access of that, would actually be provided through a set of utilities. And this set of utilities would contain that code for the access. So the process or the program would put a request, and this set of utilities would provide the access of the hardware, or rather These utilities will access the hardware on the program's behalf and will provide the result. This bundle of utilities is what we call the OS. Since the details of the hardware are hidden, that is what makes program development efficient, because the user can only concentrate on development of the program without knowing the details of the hardware. There is what we call abstraction, hiding details of the hardware. It also helps multiple apps to use or reuse the same code, because if there is another piece of hardware code called Q, another different program, and that also wishes to use the same IO, the process is the same. Whenever the program Q would be requesting this or will be requiring this IO, would also put a request to the same bundle of utility, and that bundle of utility would execute the code on behalf of this program Q. So you see that all programs or all applications which require the same IO access can reuse this particular code, which is written at a particular place or kept at a separate space in the memory. So this is called abstraction. This is the first goal that we saw. The second goal was to manage or coordinate different hardwares among applications and users. Why is this necessary? Because the hardware that is used, or we call them the resources, they are limited. They are costly and hence they are limited, because hardware resources cannot be assigned individually to each application. So they have to be shared among applications or programs. So whenever there is some sharing among a lot of programs, obviously there must be some kind of coordination or control that must be ensured. So an operating system ensures this coordination or control. And the mechanism through which it does is called virtualization. So this is the method by which the operating system makes the applications believe that all the resources of the computer system are specifically allocated to a program individual. So every program believes that it is the one which is having all the resources. However, they're actually shared, and the applications don't understand that. That's the beauty of that. Okay, so we'll just quickly have a look at this concept through a small tutorial. We have already seen this. I'll just would like to draw your attention here. Is the screen visible to all of you?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Okay, so let us quickly have a look at the concept of virtualization. And I have provided two programs to show the concept of virtualization on process as well as on memory. Let's first look at a program called CPU.C. So I will type in CPU.C. This is the program that I have. Okay, is the screen visible? The font sufficiently large?
Yes,
Is it
sir.
clearly visible?
Sir,
Okay.
font can be larger, sir. Little.
It's okay now?
It's okay, sir, but.
Okay, fine. Let me just quickly run through the code, what exactly we wish to do. It's a very simple code, and all of you are aware or you have written C programs. So I don't think I need to talk about the basics of the programming structure of this. So this is a C program which is expected to print a string. It's a very simple one. The basic these 4 lines are the 4 libraries that are going to be used to execute. One of them is the use of a standard library. The other is for a time. We can omit that for the time being. And we'll just be using this particular header file which contains some programs or with some definition of some functions in them in it. So the program says that you have a function called main, and this line is the typical signature of this particular main routine, which says that this main function after execution returns a data which is of type integer. So this first line is int, which is the return data type of this particular function called main. Main takes two arguments. One is the number of the count of the number of arguments when command line. So it's the count of the number of arguments, and that is why it has a data type called int. Argc is argument count. And second is an array of pointers, each pointing to some characters. And what are these characters? They are the arguments that you pass on the command line. So this is the typical signature of the main function. So what we do in the first if block is we check whether the number of argument count is not equal to 2. If the argument count is not equal to 2, argument count also would include the name of the executable after you compile this particular code. So if the number of arguments passed to this particular program, if it happens to not equal to 2, then it prints an error. So what it wants is it wants two arguments. Okay. One of them is the name of the program, the executable, and second one is one more argument, which in this case wants it to be a string, right? So argument, the two arguments are argv0 and argv1. Argv1 in this case is an array of characters, which would be the string that we would like to pass. And as you see, str is a pointer to that particular array, which is a pointer to that array of characters or the string. So what we would like to do, we would like to get that particular argument from command line, store it as an array pointed to by str, and then we'll scan this one by one, character by character, and would print that. So that is why there's an infinite loop which says that, okay, go on printing the value currently pointed to by str. So str is currently pointing to the first character of that particular string, or rather the who would like to print the entire string, and go on doing that. So this is called an infinite loop. So we would like to constantly print this. Okay, let's see what we have. So what we do is we'll just compile this with this particular command. So where we are typing in -o, mentioning that after you compile this particular file called cpu.c, you would be generating an executable by the name cpu. Okay, and -vol is we are going to use this particular command later on to show that when you have a number of files and you would like to, number of C files that you would like to compile, and these files have an interrelation. That is, the executable of one would be treated as an input to the other. In this case, when you have a set of such files, you may be requiring some special kind of commands. So one of them is this. For the time being, you can safely ignore that. Just understand that cpu.c gets compiled using the GCC compiler and generates an executable by the name CPU. So let's try to have this. If everything is okay, it runs fine. What I'll do is I'll just, so I would like to run the executable by the name CPU. I write /CPU, that's the name of the executable which has been created, and I will pass the argument. Remember, there were two arguments to be passed. One argument is the name of the program itself, which /CPUs have already passed. The other argument is the string that I would like to write. So let's say IIITA, and this runs the infinite loop and constantly prints the string which is pointed to by str. That's IIITA. That's what it is printing. Okay. So what interestingly happens is I have started a program. I have compiled the program, and the current compiled result is now executed. So a program is running, right? This is the view that the program is running. The program is in the memory and it is running. Let's run one more instance of the program. What do you mean by that? Well, what we'll do is, because we already have CPU, let's try to write IITKGP. So we'll run one more instance of the program. And see, this is a new program that's running, right? Well, let's look at what is going on here. Let's stop this. And okay, let me open up one more tab. Okay, so I'll just shuffle between these two terminals. As you see, IIITA is printed with the first instance of the program. What is the program name? CPU. CPU is the name of the program, right? It's the program after you compile CPU.c. We will call this a process. Okay, so we will call this CPU program as a process. So we'll have two processes which are currently executing. One that has provided an string called IIITA, and the second process also by the same name CPU, which has been provided an instance called IITKGP, an input called IITKGP. Let's see how many processes are currently running. So what we'll do is we'll just write a small program or type in a command called top. Okay. So this gives you the status of all the processes that are running currently in your system. Okay. Let us have a look at this line. If you can see, there is a command. Just pay your attention to the column called command. This will give you the different programs that are running on your system. And please try to locate a command called CPU. Okay, just look at the line, the column called command, and try to locate the command CPU. How many CPUs, how many commands with the name CPU could you locate? How many commands by the name CPU?
So four.
Four.
Okay, so I was running some already commands, so that is the reason why things were there. Let me try to use a filter on top of that to find out how many are there. So what happens is I had not stopped two programs which were already running by the name CPU. Okay, so what I should have done is, yeah, here you go. So this is what I've just run the top command, and from that I am filtering out the programs by the name CPU. Okay. The idea behind this is, let's say there are 2 or 4 or 6, whatever. Now, what exactly are we trying to understand from here? Well, what we are doing is, you see, there are 4 instances of the same program, right? 4 instances of the same program named CPU. The program was the same, CPU.c. You created 4 instances of that, right? And we will be calling them as 4 processes. Now, when 4 processes are running, are they running at the same time? Yes, they are. You see, that's what this particular command is showing me, that all of them are running. So what is going on here? So the idea is that all these 4 programs called CPU are getting a share of the CPU, okay, of the processor. All of these 4 programs called CPU, or the 4 processes, are getting their share. And they are working in a time interleaved way. For some amount of time, the first instance is getting its share, then it is taken out of the CPU, the second one is given a chance, it is taken out, the third one is given a chance. See how interestingly this is going on. Okay. So this clearly shows that even if we have 4 instances of the same program, it is actually shared. The CPU is, or the processor is shared, processor time is shared among these 4 programs. This is called virtualization of the CPU, or you give an alternate name to that as CPU scheduling. That is, you are deciding which particular process will get a chance to execute on the CPU. Run it for some time, take it out, give another person a chance, run it for some time, take it out. Okay, so in this way things go on. This is virtualization of the CPU. Let's look at virtualization of another very interesting thing, which is of the memory. So let me stop this here.
Sir,
Yes.
sir, when you typed the top grep CPU, then there were many instances of CPU. So there are every time the CPU is running, it is typing. So about 1,000 to 2,000 times CPU is running. And one
So
program,
it's going on. I mean, there are a lot of instances that I have created. Okay, I had not stopped the process. Had I stopped the process, it would not have continued. But I have not stopped the process, and there are multiple instances that are getting created. So every time you have a process being created, okay, it actually gives rise to a new process. The top command in turn goes on, executing in a loop kind, and it is creating the top command gives you a view of all the processes that are running. So my CPU program, which I had initiated, had been initiated earlier as well, before I am displaying it here. And there are a lot of such instances that have been created. And because they are constantly being created, that is why you see that the top command is showing you that all these instances are running, and there are multiple instances that you can see. Until I forcibly kill that particular process or stop that particular process, one new process will eventually be created, and that will be displayed through top. That is what is you are showing. Okay. Okay. So let's have a look
Sir,
at.
I have one more doubt.
Yes, please.
Sir, there are many numbers here. Like, what is it? Like the start time, the end time, or like there's so many numbers. I'm confused. What are they, sir?
So many numbers of what? The top command?
No, sir. Open that page now. Here, what are these numbers, sir? Like 002.
Don't worry. I'll explain everything when I'll show you what exactly is the meaning of each process and all.
So for now, we just have to see that CPU command is running again and again. This is all.
Yes. So for the time being, just try to concentrate that there is some particular command called CPU, which is, and how many instances of that are there. So for the time being, let's concentrate on that. Okay.
So sir, each instance can also be considered as a program.
Yes, I will not call it a program. Henceforth, I will define it as a term called process. Okay. This is just to make a difference between a program and a process. What is a process? A process is a running instance of a program. The program was CPU.c. That's only one single entity. CPU.c, the code that you had written. But that code has no meaning until it is executed. Right? When that particular code got executed, then you call it a process when the CPU starts executing that. Now, why do we differentiate between program and process? I'll come to that today itself. A program is merely some code and data, but a process, that is an executing program or a program in execution, has something more than only code and data. There is something more to it than code and data. It's not only the instructions and the data that you have written in your program. That is the reason why we clearly segregate between processes and programs. So the one that I was running, when I was writing CPU.c, it's a program. But when I'm running ./CPU, it's the execution of that particular program. And I'm calling it as a process. So the top command, the ones that is being displayed to the top command are processes because they are running on the CPU. Right? They are currently present in the memory, and each one of them ultimately gets a chance to get executed on the CPU. I will talk about processes and programs, the difference between the two in more details. Just wait. So for the time being, just to differentiate between the running program and the one which contains only code and data, we have made this distinction, process and programs. So processes can be many. You can, whenever you type in /CPU as we are doing, we are actually creating a process, right? We created a process. So whenever we were creating a new instance, it was actually giving rise to a process. You can have many processes which can be created. Okay, program is one. You can create many processes out of that. Is that clear?
Sir, I have one doubt, sir.
Yes, sir.
Sir, program will be bigger or process will be bigger? Like process consists of programs or programs consist of processes?
You tell me that. Think logically and you tell me. What did I say?
A process consists of programs. Is it like that? Or
You tell me. What did I say? A program contains what?
sir,
What does it contain? What does a program contain? Code and data.
program
Instructions.
contains instructions.
Instructions and data. What else do you have? It's just instructions and data that is present in a program. But when you start executing, obviously when you compile, after you compile, the compiled code or the compiled program will obviously contain instructions and data. But in addition to that, there are a lot of other things that you require. Say, for example, your code may require some dynamic allocation of memory. Is it there in the particular program? No. Suppose you had asked for an array to be defined. Did you mention from what should be has the memory being allocated for that particular array? No. When will that happen? When you will actually be putting that in the memory. So the instructions and data make up the program, but when you start executing that, there is something more that gets added in addition to the instructions and data, such as some space for the variables, some space for the arrays, some space for the dynamically allocated memory. That entire space in the memory that you allocate is what makes up the process, right? So a running instance of a program contains a lot of more things than only the program, which is nothing but just code and data. Please wait for the next chapter. We'll talk about that in details. Is this concept clear? The virtualization, that all processes that you create get a share of the CPU. Okay, let's quickly have a look at the next program, which is mem.c. And what we'll see here is it's a simple program. The basic idea is that we would like to allocate some space during runtime. And what is that? Well, the space of one integer. Okay, so during runtime, I ask this program to allocate some space, the compiler to allocate some space, and this would initially be this particular space that has been created would be filled up by an integer, and I will provide that in the in the command line. So you see, so the value that has been created, the size, the space that has been created of one integer size, only one integer size. So p is what? What does malloc return? A pointer. So p is a pointer to that particular memory that has been allocated by the compiler. Okay, what do we pass to p? We pass to p an argument which we pass through the command line. And what is that? We pass some value, which is a string, because it takes as a string and then converts into an integer. This is the function we use to convert a string to an integer, and that is what we keep in p. So what will p be pointing to? Well, it will be pointing to a particular value which is kept in that memory location, which has been dynamically created. And then we'll run an infinite loop, and the value of p gets incremented in every iteration. That's what we are doing. So what we will do is, we will first, let's try to compile this, and we will pass an argument to this particular. So a.out in this case is my process name, and I will give an integer called 0. Though I'm giving a 0, which you think is an integer, but this is treated as a string for the main function. Main takes as a string because you see, this is an argument. the arguments are taken as strings. So 0 is taken as a string. That is the reason why I had to convert it to an integer here. And then I pass it on to p. Now, if I pass this as an argument to main, what will happen is, you see what is going on. So this is the address of p. Okay, so address pointed to p. So this is the address that is being created. A particular location in the memory has been allocated dynamically, and a value has been kept in this particular location. What is that value? 0, the one that I passed. And then subsequently in the infinite loop, p is incrementing itself. So 1, 2, 3, and all it's going on. It's counting. Okay, good. So this is what is going. What is interesting is, okay, so we'll try to just rerun this, and we will try to create 2 instances of ./a.out. Okay, we will give the same value. Let's keep it the same value, and let's see what happens. Okay, let's try to argue first of all. We are creating an instance, 2 instances of the same program. So 2 processes. Remember, both process says that allocate some memory location dynamically and put a value 0 in that. Yeah, that's what the process says. Now, if you are creating 2 programs and the instructions are the same for that, and both of them says that you create a memory location in the memory location and you allocate a value to that, that means both processes should create the same memory location and should create the same value 0 to that. Isn't it? There should be some kind of, what do I say? One encroaching into the other. That's what logically we could presume that this is what should happen, because 2 processes, both are saying that, okay, create and give me a memory location and put 0 in that. Okay, one should overwrite into that. That's what should happen. So what do you think should be the output in this case? One would be writing, let's say there are 2 instances. One would start with 0, then it will increment itself to 1. By the time the other will start, the other will be making it 2, then the previous one will making 3, 4. In this way things will happen. Let's see if that is what is going on. Let's see. Oh, we are seeing that there are 2 memory locations which have been created, right? 2 memory locations which have been created, and each is keeping its own value in that, right? Let's quickly have a look. We see that there are 2 locations of the memory which have been created. So the 2 processes, even if they are having the same code, the same instructions, and they are saying that, okay, please create a memory location for me, and I want to keep some data in that. These 2 processes are actually creating 2 different memory locations, because the clear proof is that this particular instance by the number 29780, well, this is a number that identifies which process is this. There are 2 processes. This is the first process, which is having a number 29780, and this is the second process, which is having the number 29779. One is having a dynamically allocated memory with an address this, and the second one is having a dynamically allocated memory with this address. The first one, 29780, is keeping a value 0 in initializing this particular memory with value 0, and then incrementing it so that it becomes 1. 29779 also is initializing this particular address with 0 and then incrementing it to 1. So there is absolutely no problem. Each is individually incrementing its value in the address pointed to by that particular address, that particular program. Interesting.
Excuse me, sir.
Yes.
Sir, in the last tutorial, this was run by the TAs, and they told that these 2 both as addresses should be same, or they can be same also.
They can be in some cases. It's not a problem. They can be same. It's not necessary.
Or they are independent of, like, they can be same and they can be different. It has nothing to do with the program.
No, I'm coming to that. Just wait. So first
Okay.
of all, is this particular concept clear that even if you are running two instances, right? And you may, okay, so as he pointed out rightly, that this address, suppose this is the address that you are writing, both of them can be the same address. Okay, they can be same in a sense that these addresses, even if the numbers that you see are the same, okay, they are not, these two addresses would actually belong to two different programs. Let me explain this better. Okay, we come back here. Okay, so the idea here is that if this is a program called P1, right, and this is a program called P2. P1 in this case is a.out. P2 is also a.out. Now, if you remember in the last class, I discussed that every program, the moment it gets compiled, there's a set of locations, there's a set of instructions which get created. And every such instruction is given a particular address, right? Suppose there are 1, 2, 3, 4, 5, 6 instructions that have been created out of a.out. This will get an address 0, 1, 2, 3, 4, 5. This will also get an address, let's say, this will also be 6 instructions because it's the same program. This was created using the same program. So 6 instructions for this case as well. This will also get 0, 1, 2, 3, 4, 5. Look, process P1 has 6 instructions. Each instruction is getting an address. P2 also has 6 instructions because it is created out of the same code. So obviously the number of instructions will be the same. 6 instructions, same 6 addresses it's getting. And these addresses are the virtual addresses or the logical address, whatever you call them. This is virtual address and logical address. No problem. Okay. Each process is having its own address range. That's the idea. Now, when you look at the actual memory, okay, there is these 6 instructions. There is this 6 instructions, 1, 2, 3, 4, 5, and 6. These 6 instructions. They are sitting somewhere in the memory, in the physical memory. As a user or as a CPU, we are not interested to know where exactly they are sitting, these 6 instructions. We are absolutely not interested to know. It's handled by this piece of code called OS. What exactly happens here? Now, the address that you are seeing of ./a.out and the one of P, okay, so P was getting some address 0x, the second P was also getting an address this. These are actually one of these 6 addresses, one of these 6 virtual addresses that we were displaying. So the ones that were displayed as an address of P, the pointer, which was dynamically created, those addresses are virtual addresses. They are virtual addresses. And that is the reason why, even if you are running 2 instances of the program, you may see that the 2 addresses are same. It may happen. When you are looking at the virtual address of the pointer P, the address of this P, you may be getting the virtual address number 2. When you are looking at the same P in process P2, you may be getting 2 again. Yes, because when you are looking at process P2, you are looking at the virtual address of process P2. You are looking at the virtual address of the pointer P in P2. When you are in process P1, you are looking at the virtual address of the pointer P in P1, and they may be same because they are of that respective process. However, you may see that the values are updated individually. Yes, they are absolutely. Why? Because this particular piece of program and this particular piece of program are mapped to the same location in the memory. The OS is handling that. The OS handles that. Okay. As a user or an application, you don't have to decide or you don't have to worry about how it is managed. The OS, in a very efficient way, handles all this problem. Right? So
Yes, sir.
this is the basic idea of virtualization of memory. That every application is given its own range of addresses. These addresses are mapped to a particular physical address. As a user, you don't have to worry about where exactly is this mapping happening. Where is the actual program sitting in the physical memory? No need. The OS takes care of that. You just look at the address range that is generated after your compilation, and these are nothing but the virtual addresses. You see two addresses, two processes, the same pointer in two different processes can have the same address. Though they are seeing, they seem to be same address, it doesn't mean that they are actually same addresses in the physical memory. No, they are actually the addresses of their respective virtual address range. Okay. Is this clear to everyone?
Yes, sir.
Yes.
Yeah, so the final, so this is how they could control and manage the different applications. The third, advantage or the goal of an OS was to protect the data and programs against interference from other users and programs. We saw that operating systems have special programs, so it needs to be protected. And there is a clear distinction between the two through something called a supervisory control or a mode bit. So some instructions can only be executed in being in the user mode. Some instructions are executed being in the kernel mode. So all instructions related to the kernel can only be executed while they are in the kernel. So an operating system basically has two parts. One is the kernel that contains the important functionalities. And second is the system programs, which are the utilities to access the services. In the tutorial that I had just shown, I used a system program called shell. What was the shell used for? Well, this is an utility to access the services provided by the kernel. Kernel provides you the services to access files, to access the CPU, to access the memory. But for that, you need to know the system program. You need to know the system calls, which is difficult. So these are utilities that are provided to make things simpler. What are they? Well, system programs are a convenient environment for program development. Some of them are simple user interfaces. Others are relatively complex programs. Now, these system programs are used for file management, okay, for programming language support, for program loading and execution. So you can create files, you want to delete files, edit files, you just work with files and directories. Okay, so this is called the file system, the managing of the different files. Now, if the user wants to utilize the file system, it has to know a lot of system calls. In fact, we should teach you in the lab how to write, a program that would be able to do the same thing as a particular system call. So you need to know a lot of system calls in order to handle these requests to the OS. But that's again tedious, and that complicates a lot of things. So what happens is you need to give some interface, and that is why system programs are there. Okay, so you have system programs for file management, system programs for writing programs that helps users to write programs such as compilers, assemblers, debuggers, interpreters. You have system programs that help users to load program into the memory. They are called loaders. Relocatable loaders. You can shift the program when you rerun it. So now you are storing it somewhere. Next time you close that program, you restart the program, you may shift it to some other place. So these are called relocatable loaders. Linkers that connect some libraries which you did not apply during compilation. You want to include those libraries to your program at runtime. So that is done through a special kind of a program called linker. For example, when you write hash include stdio.h or maybe hash include math.h, and you wrote a C program where you would like to include some mathematical functions. You take help of some third-party libraries in C. One of them is math.h, and you include that. Well, all the functions, math-related functions that you would like to execute get linked to the functions defined in math.h. So these are called programs known as linkers. Okay, they help you in writing programs. Then there are programs that help you in communication, such as your chat programs, your web browsing, your emails, remote login. You would like to connect from one computer to the other. You need to write some programs for that. Now, if you think how complex things would become if you have to write all the system calls and then do that, it's very, very tedious. So you need some programs which would actually help the users. So users would write some simple codes or simple commands, and they in turn will be, translated into the list of system calls, which will be executed by the OS or the kernel. Okay, status information. We just saw one of example, top, PS. So in Unix, we have these commands which help you provide the status information. What is going on in the system? How many processes are running? What is the space? What is the date, time, etc. So all these commands are there. These are all programs. Each one of them is a program. The top command, the PS command, they are given to the user in the form of a command, but they themselves are programs. What do these programs contain? Well, they contain list of system calls that eventually allow to perform the task that you intend. Okay, so these are different system programs. So how does the how do the users interact with the OS? The users interact with the OS through two different ways. One is called the command line interface. So these are the different interfaces given. Command line interface is you have to write commands in order to pass on the information to the kernel. So the command line itself performs different functions, or it can call other system programs, right? So in Unix, we have this famous program called the shell. So whenever in the terminal, this terminal, the name of the program is terminal. Whenever you click on that, what you give is there's a program that gets invoked, and the program is called shell. All Unix-based systems have a shell. So what do you do there? Well, the shell is an interface through which you ask the kernel to do some task. What task? Let's say the moment you turn on the shell, you get something like this. This is the prompt, and it waits for some command. Suppose you type in a command called ls. ls means list the files and directories of your current working directory. So what you are doing is you are asking the kernel to execute or to run some system calls and get you some information about what are the files and folders which are there in your present working directory. That's what you are doing. Okay, so this is the way in which you will be able to tell the kernel to do some task. The other way is the graphical user interface. We don't write commands. Rather, we have some click interface. We have this device called mouse, and that takes or allows the user to select a particular portion of the screen. And if you click on that, this eventually invokes some event, and that event is equivalent to writing a command on the command line. That's what it is. So eventually what happens is when you click that, a command is invoked in the background, and that command eventually is nothing but a program, and that program contains a lot of system calls written in particular order. And if the system calls get executed, the hardwares are accessed, and whatever you intend to do gets done. So Microsoft Windows is the most popular GUI based operating system. Macintosh is there. Then we have different variants of Unix today which are available. One of them is Linux, which is very, very popular. One which was introduced by Linus Torvalds. So he's the one who's responsible for development of the Linux kernel, and then subsequently, different system programs were added to that, and different variants of Linux have today evolved. But the basic kernel is still the Linux kernel. Linux was developed from Unix. The basic idea of Unix kernel was introduced, and then with it, some modifications were made. So the Linux kernel, along with its whole bunch of system programs together, is the Linux operating system. The way in which those system programs are provided, or the different type of system programs which are provided, that differentiates the different flavors of Linux. You have Ubuntu, you have Fedora, you have SUSE, you have Arch Linux, you have Kali Linux, you have embedded Linux. So different kinds of, the variants in which these particular tools have been developed, the system programs are provided, and how they can be accessed, how they can be used, that differentiates the different flavors of Linux. But all of them, ultimately, the kernel is the same, right? It's the Linux kernel. Then the third way to run is through something called a batch, or we call it the script. What is that? It's again the command line itself, except that you don't write one by one the commands. You write all your commands in one single file, and through a third command you run that. Say, for example, I have a file, I write a file, and in which I write some commands, let's say ls, then cd, then mkdir. I write it in this way that these are three different commands which I can type one by one. Instead of that, I write a test.sh, and this is called a script file. So I put down all my commands in one particular file called the script file, and then I go to the Linux terminal in the shell, and I type in, okay, sh test.sh. So what I do is, I am asking to execute this particular script. What is this script? Well, this script is nothing but a list of three commands. So these three commands will be executed one by one. This is called a batch. It's like I collect some commands in one file, and then I execute the file. So all commands in that particular file get executed. This is called batch executing commands, or we call them as the scripts. So what we have is the commands are given using a file or a script, and then they are executed. These are called shell scripts. It will be explained about shell scripts the time. Just wait for the lab where we'll show you how to write shell scripts. Okay. We have the next concept that we are going to talk about is called system boot. Okay, this is again a very interesting thing that we would like to know. All Unix-based OS have the same kernel, not Unix-based. Unix is the same kernel that is modified to come up with the different Linux. You're talking about difference of the kernel between, say, Mac and Linux. Is this the question?
Yes, sir.
Okay. To some extent, same. I wouldn't say. I mean, majority of that. You can call it that Linux is a subset of Unix. some part of the kernel has been, they are actually derived from Unix, both Mac and Linux. The way in which the kernel handles the different system calls, etc., they are same. Some may be different. The way in which the files are managed, that may be different. The file system handling, the scheduling part, that may be different. Okay, but the basic idea of working with process creation, that may be same because it's derived from there. Okay, so majority of things are same except that some portion of the kernel may be different for Mac and Linux.
Sir, I don't understand this. Are derived from Unix, and sir,
Yes.
like what is like derived like Unix? Like why can't we use Unix directly? And
You can.
Like-
Who stops you? But the problem is
Oh.
that there's a lot of things that you cannot do that has been modified in Linux. You cannot run a lot of applications. The basic problem of the initial Unix was that there was no support for GUI. And that is the reason why people felt a bit uncomfortable while handling that. There was no desktop manager support for that. The graphics was a bit difficult to handle. Okay.
And sir,
So that
Unix
is
and
why.
Windows are completely different.
Huh?
Unix and Windows are completely different.
Which one?
Unix and Windows.
Yeah. They're completely different. It's a different way of the two kernels are absolutely different. The way in which the different components are handled in Windows. Well, I'll give you a small example. If you talk about the file system, I mean how both of these handle the files and folders. Windows is a multi-rooted file system. So if we have something like C, D, right? Whereas in case of Unix-based systems, it's a single rooted tree. Everything starts from root, and then you have USR, OPT, DEV, okay, and then we have something called home, and within that you have desktop, or maybe okay, so directly desktop you have something like IIITA, a student, and within that you have desktop. So this is the way in which files are organized in a Unix-based system. It's called a tree structure, multi-rooted, single-rooted tree. And here you have multi-rooted tree. We have a partition called C. You have files within that. You have D, and they are independent. So that's C. That's two
Sir, and
ways
which one is better, sir?
It's difficult to say. There's nothing called better or worse. There are two different ways of implementing things. It's just the way things work. If you want to know personally about me, I have been using Unix-based system. I normally do not use NTFS file system. So this is an way of handling. This is called NTFS, and this is called ext3. These are two different file management techniques. Windows uses this, and Linux uses this. I prefer this one because to me, it's the more logical way of handling things. But however, okay, there's no argument. This can as well be, some may feel this to be better, whatever.
Sir, what does mean by NTFS and ext3?
These are two names given to the two ways of handling files and folders. This is called a file system. File system is the way you organize your files and folders. You see, this is one way of organization. This is called ext3. And this is another way of organizing things. This is called NTFS. We'll talk about that later on, how files are organized using NTFS. It's a table where there's a table that is maintained which keeps track of where the different files are and how do you access those files. Whereas in case of Linux, it's simply, it's a bit different. It handles it in a table of content way. So we'll talk about that when we come to file system. Is just an idea that the way in which you organize things may be different for different kernels. So, but if you look at Mac and Linux, both use them. So the way of organizing files in Linux and Mac is the same as this structure. So that is why clearly you can see that the file system is derived from Unix. The basic Unix structure is maintained in both of them. On top of that, they can have different ways, different applications, different system programs that may be different. But the basic, structure of handling the files is the same. That is the reason why I say that, okay, it's derived from that. But you see, look at the Windows, it's completely different. That is, I'm saying, that is the reason why I say that, okay, these are all variants of Unix. There are other, from OS modules as well that you will find that it is derived from Unix, whereas for Windows, it's completely different. Okay. Let's talk about the second, the important part. So now, how does an OS get loaded on the primary memory? Okay. Operating system is in itself a program, correct? So the operating system is a special program, but that also has to come and get loaded in the memory. We just saw that the basic idea of program execution is that any program, whatever be the program you want the CPU to execute, has to be loaded onto the memory, the physical memory. That's the rule. So if OS is a program, that also has to come and get loaded in the physical memory. So the process of loading the operating system or the kernel onto the physical memory is what you call booting. This step is called booting. Okay, that is why it's called. And until you get this fellow into the primary memory, no processes can execute, because a process called P1, you have developed a program, you've written a program, you've initiated a process, and that gets loaded. But it will require some system calls, isn't it? And the system calls have to be asked to the OS. So it's obvious that the OS should be present in the physical memory. Only then the request can be put. So if you look at the order in which program should be loaded in the memory, the OS should be the first one that should get loaded before you load any other program in the memory. Because all programs will need help of the operating system to carry on their operation. So it is obvious that the operating system should be loaded first. The kernel should be loaded first. Now the question is, how does this whole process begin? Where does the OS reside? Okay, the OS, it resides in the secondary storage device. Okay, this is where your OS resides. Let's say, for example, the hard disk. Now here we should see some structure of the hard disk first of all to appreciate that what goes on. So the operating system is a program, not the process, the program, which is residing in the secondary storage device in the hard disk. How? Well, let's look at the structure of a hard disk. The hard disk is a magnetic disk. You all remember the DVD drives? It's a magnetic disk, right? And that is divided into number, or it has a number of concentric circles. It's like this. And they are called tracks, right? And these tracks are divided into number of segments. These are called segments. Okay, so this is a segment. Fine. So if you want to keep some data, it has to be kept in the segment. And interestingly, this particular hard disk is a block device. That means whenever you read some data from the hard disk, you are actually reading the entire segment. So the data that is read from a hard disk is read as a segment. You read the entire segment. You cannot get a single byte. You have, when you will be reading, you will be getting the entire segment. How is the data read? Well, that's a very interesting thing. This is, let's say, the disk. Now what happens is there's a spindle, okay, and there is a, this is kind of a head. We call it a head that just touches this particular surface of the disk. So whenever there is this head comes just above a particular segment, it reads the entire segment, and that's the data that has been read. So it's like this. It just touches a particular portion, and then the entire segment of that gets read. Now, to move on to the, so let's say this is the head that is pointing here. Okay, so it's reading the entire segment. Now, if the disk rotates, then the head is fixed, the disk is rotating. So now this segment moves in below the head, and the next data gets read. So it's like sector 0, sector 1, sector 2, sector 3. In this way, things are read. Okay. Now, this is how there are multiple disks and there are multiple heads. So all of them are, reading at the same time. It's like this, and all these are arranged in a cylinder. This is how things look. Magnetic disk looks like. So there are disks and there are heads which are touching that, and there are multiple disks, multiple heads. So number of sectors are read at the same time. But whenever a head is on top of a particular sector, that's segment or sector. I should say sector. Let's call it a sector. A sector gets read. Read as sector, not segment, sector. Clear? Okay.
So sector is whole triangle or just it contains three sector. One triangle contains three sectors.
No, it's you divide that into, you take a cake and you cut it into number of halves, right? So that every half that you get, that's what you call a sector. This entire thing is a sector. A sector encompasses a lot of tracks. In this case, in the figure that you see, this is like, okay, let me draw this again. So our disk is, this is a disk. This will have number of tracks. If you divide it in this way, this portion, this is one sector. Let's say it's sector 0. This is another sector. Sector 1. Sector 2, sector 3. So a particular disk can have many sectors. And a sector can contain data from track 0, track 1, track 2 in this way. Clear? Sector 0 is of size usually 512 bytes. And this is a very special sector. This contains some very interesting, information about the hard disk. We'll talk about that. So the hard disk resides somewhere here. Maybe, the operating system resides in some part of the hard disk. It may be in the first days, second days, third days. Please understand, it's not necessary that the entire operating system program will be residing in one disk itself. It may be distributed all through. Somewhere maybe here, somewhere here, somewhere here, somewhere here, all this. It can be absolutely in a distributed way. And I will call them as sectors or blocks, whatever. So let's say the entire OS code is maybe made up of a number of blocks. Block 1, block 3, block 5, block 9. So a lot of blocks together are totally forming the OS code. So when you want that particular code to be loaded, that has to be brought from the hard disk, and then this entire thing has to be brought and loaded into the primary memory. Correct? So let's say this entire thing, you collect it from here, from here, from here, from here, collect everything and put it in this particular portion of the primary memory. This process is called booting. Okay, so the OS code which is residing in the hard disk has to be brought into the primary memory. That's the booting. How does it take place? Let's look at the steps. First of all, the operating system must be made available to the hardware so that the hardware can start it. That's what we want. Okay, so the first step, I'll just mention the steps one by one, and then we'll see. Okay, so the first step that goes on is called power on reset. That means you turn on the power, right? So let's say you turn on the computer. You press the power button of your computer, and what happens? Okay, the moment you turn this on, your CPU, which starts executing. The moment you turn on, you actually have powered on the CPU. OS is still not there. You just have powered on your CPU. The moment you power on your CPU, now CPU has some registers. Okay. CPU has some registers, a lot of them. Some of them are very special registers. Why? Because they are actually pointers to certain memory locations. Right? That is why I'm calling them as special registers. One of those special registers is something called a register called CS. CS is by the name code segment. I'm talking about an Intel machine. I assume that it is an Intel processor. So there is a register called CS, which is a register that contains something called code segment. It's an address. It holds an address. What is an address? Whose address? Well, address of a particular memory. I'll come to this memory later on. So for the timing, it's a pointer. It is pointing to a particular address. So this fellow gets initialized, this code segment. As the name implies, it's a pointer to a code. So this code segment register that gets initialized. So I just write it here. I'm not mentioning the details. A lot of registers, they get initialized. Some values here get written the moment you turn on the power. One of them is the CS, some value. And this CS, it is some operation happens. It gets shifted by 4 places. And then you add some instruction pointer to that, which is an offset. You don't have to understand the detail. Just remember that some registers get loaded with a particular value the moment you turn on the power, and that's fixed. Whenever you turn on the power, this register will always get loaded with that particular value. That is fixed. What is that? Well, that is what it is. It takes you to a particular part of the memory. That actually points to certain memory, and this memory is interestingly a read-only memory that is also present along with the CPU, and it is present on the motherboard. So here we have the motherboard, and there's a within that socket itself there's a small chip that is there. It's a ROM, read-only memory, and whenever you initialize this CS, it always points to this particular first location of the memory. And this special ROM is, we know it by a name BIOS. Okay, it's called basic input output setup. So this particular memory, this pointer points to a particular ROM. Because it's ROM, it's fixed. It always points to the same location. And there is some program that is written there, and it's called BIOS. BIOS means the basic input output setup. So this takes you to. So I write it as register initialization. Okay, and then we go into a BIOS. What is this BIOS? It's a small chip, right, which is connected to the processor. It's a memory, right? And what do we have here? So it's usually ROM. I'd say it may be either flash. So what is the role played by this ROM, by this BIOS? So it has some roles. The first one is, it's called power on self-test. or we usually call it host. We see whether all devices that are getting connected or connected to the processor, are they working correctly? Everything blinks for once the moment you turn on the power. This is a check that every device is working correct. This is called power on self-test. The BIOS run this program first. Okay. Then we have some initialization that happens. It initializes the video card. What is a video card? Well, the hardware controller that is associated with the all the video units. It initializes the video card, the network card, okay, and other devices. Whatever, there's a network card, there's a keyboard controller, everything. All these are programmed the moment the BIOS starts running. Then it displays the BIOS screen, right? And you see a lot of things scroll. The moment a lot of things that get scrolled. So that's like a lot of initialization is happening. And then you have it configures the plug and play devices. So all those devices that you have connected, that gets programmed. They are initialized. Okay. And the most important thing after this they do is it identifies the boot device. Now, all those who have programmed your BIOS or have used the BIOS, you will see that there is an option to select the boot device. Whether you want to boot it through a hard disk, you want to boot it through a network, you want to boot it through an USB drive. So there's an option to select in BIOS. So you are able to identify the boot device, and according to the default setting or whatever the user has selected, it identifies the boot device. Let us assume that we have identified that my boot device is a hard disk. Done. This is what the BIOS is supposed to do, right? So now that you have, this particular execution, the BIOS has executed, the boot device has been identified. Boot device is, let's say, this my hard disk. Here, somewhere here, my is been identified. Well, that's the first thing. So the boot device is identified, and now you jump to that particular location. So now this is the RAM, the memory. Okay. So what you do is the program counter here, it jumps to a particular portion in the memory. Okay, that's what you do. And this particular piece of program in the memory where you jump to is called MBR. So BIOS, at the end of execution of the BIOS, we jump to something called MBR execution. MBR execution. What is MBR? MBR is called Master Boot Record. Yes, that is correct. It's called Master Boot Record. What is this? Well, it is nothing but the sector 0 of the hard disk. Did I tell you about this? Sector 0 is the most important part. What is the size? 512 bytes. 512 bytes only, not MB, 512 bytes. Out of this 512 bytes, 466 bytes, they are bootable code. Okay, information about what is to be done during boot, that's what is there. 64 bytes are for the partition information. That, okay, you are asking me to load the operating system, but I see that in hard disk there are 3 operating systems or 2 operating systems which are sitting, and Windows or NTFS as well as ext3. Which one should I load? So that will be told later on. First of all, it is just an information. So 512 bytes. So in the hard disk, this 512 bytes itself contains information about what to do during boot and what are the partitions that are present in the hard disk. This information is there. So think it is like a blueprint. Until you read that, you don't understand what is there in the hard disk. So this is the information that should be read. This 512 bytes are first read into this particular portion of the memory in the RAM. This is it is brought into the memory. So the moment BIOS is over, the first 512 bytes or sector 0 code is brought into the primary memory, and that is executed by the CPU. When CPU executes that, it first goes to the 466 bytes and knows, okay, this is the bootable code. Then 64 bytes are read to understand what is the partition. And then we have 2 bytes for signature. Just to know that, okay, this is indeed the correct MBR. This in total makes up the MBR. Okay. So when the CPU goes through this 512 bytes and this executes this, or the MBR is executed, it understands, okay, these are the partitions there in the hard disk. These are the different operating systems which are present, and that is what is done after MBR gets executed. Okay, so now the MBR is executed, CPU knows the partition.
Sir,
Yes.
what is signature?
Signature is kind of an additional bytes that are kept to decide whether it is indeed the correct MBR and it has not been tampered. So just to keep an authenticity of the code, we keep some signature. If that gets tampered, we mean that, okay, this is a wrong MBR and you should not take it. Okay. When this MBR gets executed, the next thing that happens is, now that the CPU is aware of what is the partition in the hard disk, now it is time for us to decide or to load the OS. But again, as I told you, there can be 2 OS, multi-boot system can be there. So they can reside in the hard disk. So how to decide which of the blocks in the hard disk now you should bring in? Should you bring the blocks that refer to the Windows operating system or the Linux? That is done through something called Bootloader. This is also a program. What it does? Well, it loads the operating system. Okay, it loads the operating system. Usually, MBR itself is, in some cases, MBR is sufficient to load the program or tell that, okay, this is from where you should bring, this is the sectors that you should bring into the memory. Or MBR, in some cases, takes help of this special program called Bootloader. An example of this bootloader is a typical bootloader program that we often use is called Grub. So all those who have, all those who have used multi-booted systems, you may see that a screen comes up, a screen pops up, and that allows you to choose between whether you would like to boot the OS as Windows or you would like to boot the Linux OS. So that program that displays and gives you the facility to load is part of Grub. Okay, that's called the bootloader program. Okay, so bootloader program, it allows to load the program, and it often allows the user to select the boot OS. Right? Where does the bootloader reside? No, it's not the name of the screen. The screen is part of that Grub. Bootloader it's only one of the display programs of Grub. It's not, usually.
Sir, I have one more doubt. So you said bootloader gives us the option to load which OS we want to load. But sir,
Yes.
all the information you said is also contained in MBR section, that which
I'm
operating
coming.
system is there.
I'm coming. Bootloader is actually part of MBR. So
Okay,
the bootloader is usually present in MBR. Okay. So that is in the sector 0 itself of the hard disk. So once we have the bootloader ready, now you have the OS, and so in some cases the bootloader also enables and disables the interrupts, etc. So once the OS is there, now you have something to do. OS means the kernel, right? I'm talking about the kernel first. So you have setting up the virtual memory, the first job of the OS. First and foremost, set up a virtual memory. You initialize the vectors. Yeah. The interrupt vectors. Then you initialize the monitors. Okay. We have the timers. You initialize the timers, the file system. So that's the job of, and you start the user process. Okay, so as somebody asked me, what is the bootloader? Well, bootloader is a program that allows the user to select among different operating systems. If you have only one operating system that is there in your program, you may not require, or maybe you will require that. So bootloader is a program that actually gives instructions to load the certain sectors from the hard disk into the memory. Which sectors? The sectors that contain the kernel of the OS that you would like to load. So let's understand it this way. MBR is the blueprint. It contains 512 bytes. It gives you an idea that, okay, this partition is from this sector to this sector. This partition is from this sector to this sector. Now, who will tell the instruction? I mean, who will provide the instruction that, okay, let's say MBR has an information. Let's say the MBR code. The MBR code is like this. Say kernel 1 is from sector number 0 to say 400. Okay. And kernel number 2 is from 500 to 800 maybe. This is the table that is maintained in the MBR. Now there's a program called bootloader. Now after this, so bootloader would provide the user an interface through which the user will be able to select option number 1 or option number 2. When user selects option number 1, you are actually selecting, let's say, this particular option. And this option means sectors from 0 to 400. So bootloader passes on an information asking to load the sectors from 0 to 800. So the CPU now would ask the DMA controller to load the sectors, the contents of sectors 0 to 400. So this, what is this program? So it facilitates the user to choose among the different kernels. How? It gives you a screen and it gives you an option to select those commands. So selecting the command is actually invoking or selecting one of the options of the table. And accordingly, bootloader provides an instruction mentioning what to do, which blocks from the hard disk to be loaded. That's what is the. So bootloader gives you two facilities. Number one, it actually loads the program. It gives the instruction to the DMA controller, to the CPU to load those data from the hard disk to the memory. If there are multiple operating systems that are there residing as read after the MBR, then it also gives the user the facility to choose which one should I pass. Should I give this range or this range? If there is only one, there's only one entry in the table, so it will be sending out the default range. Okay, this is the utility of the bootloader. It actually loads the program. Clear to all? So power on reset initializes a lot of registers in the CPU. Some registers which are getting initialized are nothing but pointers to a particular chip or a ROM, you can say, which contains a special program called BIOS, which actually sets up the environment for loading of these applications. So the BIOS performs, first of all, a test of all the devices that they are correctly connected. The hard disk is actually well connected. Once it is done, then it loads the first 512 bytes. Those 512 bytes of the for sector 0 of the hard disk gets loaded onto the primary memory, onto the RAM, and those 512 bytes are executed. These 512 bytes are the most important part of this OS, because it actually contains the blueprint of the entire hard disk. What is the some instructions regarding the booting process? What are the partitions present in your hard disk? So after, and some cases it also contains a special program called Bootloader, which is actually the program that loads the kernel onto the primary memory after it consults the MBR table. So it looks up to the table, finds out, okay, this is what the sectors are. From this to this means OS number 1, this to this means OS number 2. So if somebody wants to load OS number 1, I actually have to load these segments, the sectors from the hard disk to the primary memory. If it is OS number 2, I have to load this sectors from hard disk to the primary memory. Accordingly, it also provides an interface to the users to choose that. According to what the user has chosen, it selects the range and asks the CPU to load it into the primary memory, or rather the DMA controller to do it. Once it's done, the kernel is now into the primary memory. And the kernel is now into the primary memory, the kernel is supposed to do certain initialization. First and foremost, it initializes the virtual memory, because without that, no application can run. Second, it initializes certain interrupt vectors, because all system calls will be provided through interrupts. Third, it initializes certain timers, some file system, and it starts the first user process. The first user process that starts is usually called a program named init. So the init process begins. Okay. The init process in turn starts other processes. We'll see how one process creates another process. The process that handle the networks, they run in the background. They're called daemons. Okay, so that's how the OS begins. So we discussed a lot about process. What exactly is this? I've already made this clear. Whenever you start running the program or a program gets executed, you call that as a process. More of that or more details about that I'll come to in the next tutorial class. So OS allocates the physical process address space. Just saw that. A program is nothing but some code and data. That's what it is. But when it actually gets converted into a process, it's not only the program and data. It has some stack that is there. It has some heap, some space for containing the variables. Then it contains the code and data. So the range of addresses get allocated. So this is say CPU.c, a program, and when that gets converted or compiled, so when you write gcc CPU.c or mem.c, let's say there's a program called mem.c. So this was residing in the hard disk. When you compile that, you get converted into a program called a.out. And this a.out program, when you load that into the memory, when this gets loaded onto the memory, there's a space of or a range of locations that is allocated to that. This is called the address space of the process. The moment you load that in the memory and it starts executing, it becomes a process. It's a program in execution. Program when it starts executing. And the program when it starts executing, not only the space is given for code and data, but something more, space for stack or heap, because there may be situations where you have used a malloc in your program. Malloc is a space that you want in the memory. When will that be given? At runtime. So it will be given space from this portion of the memory. So there's a range of addresses that automatically get allocated to this particular process. Okay. And that amount of space that is allocated is called its address space. What do you have in this address space? We call it the memory image. The entire thing that resides in this allocated. No other process will be allowed to write anything within that range. It's called the memory image. What do you have in that? We have the program, the data, the stack, the program status word, heap, linked libraries, everything, all this. Okay. I've already discussed about virtual memory in the previous class. So we already have seen that how every program gets a range of addresses and they are actually mapped to the physical address. That's what we call the process, the virtual to physical address mapping. Okay, we have already seen this as well, how a program executes in a dual mode, right? Because processes share the space, there is every chance that one would disturb the other. So the solution is you must restrict the code by a dual mode of operation. How? You give two privileges. Either you give the user you call it the user mode when all programs can run, or you give a mode called kernel mode only when the kernel programs would run. And there is a shift between or a switch between the two. How? Obviously through something called interrupts. So the interrupts will transfer the control to the interrupt service routine, and those interrupts get executed. Okay. So I would actually stop it here. I'll take up this in the next tutorial class, in the next week. And I think we now have a basic understanding about how an operating system works, how it gets started, and what is it basically used for. Okay. So in the next class, you will be introduced to the concept of process. And then in the tutorial class, I'll be taking up the idea of how system calls are executed. We'll look at different processes, and we'll also see some basic, we'll look at the process memory image of a process. We'll look at every components of that. And we'll see how we can create one process from the other. Okay, so I'll stop it here.
Sir, can you